Hello everyone. So today we are going to start a lecture on that is calculus of variation, which is in your unit 5, right? So this is your unit 5, right? So what are we trying to do is, what is calculus of variation? So we are going to find that is in calculus of variation primarily deals with what? That is finding, that is maxima or minima value of a definite integral, right? Definite integral involving certain function, right? So before starting with the concept, let us know what is this maxima and minima, as you have done in your earlier classes, as is plus 2 classes, 12th or PUC 2 classes. So this is just example which I have taken. Okay, show that y is equal to x power 5 minus 5x power 4 plus 5x cube plus 1, right? So this is your y and this is your f of x, right? So as maximum at x equal to 1, minimum at x equal to 3, and neither maximum nor minimum at x equal to 0, right? So here what we did is we are going to find minimum, maximum. So all in that this example is being taken uh, for your understanding purpose only, right? So given equation is this, and then you find in the given equation, if at certain instant any other given equation, if it is given in terms of y is equal to f of x, and then you take first derivative test and second derivative test to find it, that is maxima or minima, right? So when you differentiate it with respect to x, so it is dy by dx and this 5x power 4, and finally you have this, right? Again when you differentiate this with respect to x, that is d square y by dx square, which is equal to 20x cube minus 60x square plus 30x, right? Now at x equal to 1, okay, so what is this dy by dx? That is, you substitute over here, that is at x equal to 1, it is equal to 0. Now d square y by dx square, so 20 minus 60 plus 30, which is equal to minus 10, which is less than 0. So if it is less than 0, then y has maximum at x equal to 1, right? So at x equal to 3, it is 0 and it is 90, and which is greater than 0, and we say that y has minimum at x equal to 3, and at x equal to 0, dy by dx equal to 0, and d square y by dx square, that also turns out to be 0. So we conclude that y has neither maximum nor minimum at x equal to 0. Now also what we have is, fine, so here what we do is, so y is equal to f of x for any given function, we have find that is maxima or minima. Also when you come for higher section, that f is a function of more than two variable, right? Right. So we have find maxima and minima for this type of problem also, right? Now before dealing that is starting with the definition of functional or variation problem, we shall see what is this functional, right? Now let me have an simple example, right? Simple example of functional is the shortest length of a curve through 2 points, that is a is equal to x1 y1 and b is equal to x2 y2. Okay, in other words, the determination of the curve, that is y is equal to y of x, for which that is y of yx1 is equal to y1 and y of x2 is equal to y2, such that that is the integral over the limiting points, that is x1 and x2, is square root of 1 plus dy by dx the whole square dx, which is your equation 1, is minimum. This is just an example. Fine. Okay. Now what will happen? I need to find the shortest distance, okay, over these two curves, that is y1, y2. These are curves. This dotted line, when you can see, these are curves. Okay. Now it so happens that, so what I'll do is, this is an example of derivative of an arc length, right? So what I need to find? I need to find the shortest distance, and which is given by, that is square root of 1 plus dy by dx square, square root of 1 plus dy by dx square the whole square dx x1 x2, right? And to which the value is minimum. So this is the geometrical interpretation. Okay. Now integral of such type, that is equation 1, is known as functional. Now let me tell you how it works. Now what I do is, see here, any point on this curve, right, whether it is y1 of x or y2 of x, right? So what I do is, this is my surface or the arc length s, this particular thing, right? Right. So what I'll do is, I will take tangent over this, some part. I'll draw tangent. You can draw here, you can draw here, you can draw here, right? And this is x1, and this is my, that is x2. Some portion of the curve I will find its taking that is its arc length, right? So now this equation here, this is some part of, that is y, that turns out to be dy of this y, this is some part of dy, and of this x, this is some part of dx, right? And this is, for this curve, this is some part of ds, right? Now for this particular thing, okay, how do I evaluate it? So this is the concept of derivative of arc length. So I need to find the shortest distance. So if I take any point and take tangents, okay, some part I'm going to evaluate so as to get the length, okay, length of this particular curve, right? So everywhere it is not same, here it is not same, here it is not same, and this is, and these are the points, that is x1 x2. I need to tell you the concept of what exactly is this, that is functional. What do you mean by functional? Okay. Yeah. Now this ds by dx, let me show it. Okay. Okay. So see here, this is how we are doing it. Right. So this is my curve, that is length of the curve. If we want to approximate the length of the curve over a short distance, we could measure a straight line, right? Now by Pythagoras theorem, we can say that is, it is ds by ds square, right? So ds square is equal to, that is dx square plus dy square. Now ds square is equal to, which is equal to square root of dx square plus dy square. Now how we are going to find the length, right? Okay, this will be, yeah, this is much more better. So arc length of the surface area, see here, this is a and this is b, wherein in a problem this is x1, this is y1, and here it is the short, this some part of this curve, right? So either to find its maximum or minimum, or that is, it is minimum, right? So here if I am taking this particular value or some part of it, so by Pythagoras, this is ds, that is I am taking, drawing a tangent over here like this, right? So it is ds dx dy. So ds square is equal to dx square plus dy square. So ds is equal to square root of dx square plus dy square. Now but dy by dx, I can write it as f dash of x, okay, so that dy is equal to f dash of x is equal to dx. I can write it in this particular manner. Therefore ds is equal to square root of dx square as it is, plus this dy square I can write it as f dash of square dx square. Now here dx square and this dx square, this common, I take it outside, so it becomes 1 plus f dash of x square dx. Therefore arc length over the interval, that is a to b, that is limit, and it is ds. But what is the value of ds? That is, it is square root of 1 plus f dash of x square dx, and that is what here it is given as this thing, that is 1 plus, that is f dash of x square, here it is d, and that is f that is dy by dx square dx over the interval, that is limiting points x1 and x2. So any integral of this type, okay, is called functional, right? Fine. So in general, so here comes the definition of functional. Okay, so in general it is required to find the curve. So what are we doing is we are finding the curve y is equal to f of x, where y of x1 is equal to y1 and y of x2 is equal to y2, such that for a given function. So what happens for any given function, any function of the type f is a function which contains the variable x, y and dy by dx over the limits, that is over the interval, that is x1 to x2, dx is maxima or that is minima. Now this equation 2 is known as functional. Now what will, that is any equation of this type is known as functional. Now which is denoted by, see, I, in few textbook it is written as I y of x, right? Yeah, which is equal to, the functional is defined as integral of f is a function of x, y, dy by dx and the derivative with respect to dx over the interval x1 and x2. This is a functional to which we are finding what? We are finding, after evaluating this, we are getting equation of the form, that is y is equal to f of x. Now to this, now for this equation, the above equation is an extremal, that is it is maximum or minimum, right? So after evaluating this functional, we are getting a function for which the above function is maxima or minima, and it is known as, this equation is known as, that is functional, right? Getting? So any equation will be given in this form, and we are going to find its output in terms of y is equal to f of x, that is another function. So this function, okay, this function, now for this function, this functional is an extremum, that is whether it is an maxima or minima. Now we are in the note section. Here it is, in differential calculus we find maxima or minimum value of functions, but in calculus of variation, which deals with the problems of maxima or minima of functional, and the functional is, that is any given, that is function of the type, the given function is in terms of x, it is y, and it is the derivative with respect to dx, okay, over the interval, that is x1 comma x2. So we are going to find what? Maxima or minima of this particular function, wherein after evaluating this we get equation, that is y of the form, that is after evaluating this we get an equation of the form, that is y is equal to f of x, for which the given function is extremum, right? Now a functional, so usually we represent it by I y of x is said to be linear if it satisfies if it satisfies the first property is, right, I of cy of x, so where c is constant, so I y of x where c is arbitrary constant. Now I of y1 of x, if they are two functional, so I y1 of x plus y2 of x, which is equal to I of y1 of x plus I of y2 of x, right, where y1 belongs to m and y2 belongs to m, where m is nothing but either it is maximum or minimum. Now here comes the definition. Yes, this might, okay, a functional I y of x is maximum, right, if it is said to be maximum on a curve y is equal to y of x, if the values of the functional on any curve close to y is equal to y1 of x do not exceed I, that is function I y1 of x. It means that the difference, that is delta of I, is equal to difference of the functional and the curve close to, okay, that is functional I y of x minus I of y x1 y of x1, it is less than 0. Okay, and for the minimum case this turns out to be delta of I greater than or equal to 0. Fine. So this they might ask you in quiz, right? Now let us see an important concept, that is what is this Euler's equation. Now this Euler's equation is very important in solving variation problems, right? Any variational problems can be easily solved by making use of this Euler's equation. Okay, now we shall see what is this Euler's equation. So this equation, Euler's equation, is very important in solving that is problems pertaining to, that is variational problems, right? So we shall see what is this. Fine. So a necessary condition, that is Euler's equation, that is a necessary condition for any given functional, that is written in the form of I of y of x over the interval that is the limit, that is x1 x2, wherein f is a function which contains x, y, y prime and dx. Let me consider this as equation 1. Is said to be extremum, either this equation is maximum or minimum, is that this Euler's equation should satisfy, that is dou f by dou y minus d by dx dou y and dou f by dou y prime is equal to 0. And this equation is very important, so please have a note on this. Every now and then whenever we are finding that is solving problems of variational problems of a functional and we make use of this Euler's equation. So pertaining to this we also have that is some other forms of Euler's equation, right? So let us see what are the other forms of Euler's equation. Now since f is a function of x, y and y prime, therefore if I take the total derivative of d, that is f along x, right, so df by dx, so after evaluating I get, that is taking total derivative, so it becomes dou f by dou x d by dx. And so this is the explanation part is here, right? So this is how it goes. Here this I have written because my writing pad is not working, so kindly adjust, right? See here, this is the total derivative. So f is if I want to take the total derivative from f to x, so if I f is associated with how many variable, it is associated to only one variable from year to year, right? And this complete thing I need to find the total derivative of df by dx. Since it is associated with only one variable, I am writing d, and if it is associated with more than one variable, then I write dou, right? See here, I want to take the total derivative from f to, that is f to x, right? So from f to x, right? So from f to x, what is how many variables? So it is one variable, so that is the reason I write df by dx. Now see here, now f is associated to how many variables? 1, 2 and 3, so I write dou f by dou x. I take this arrow first, so dou f by dou x, right? Then from x to x, how many variables are associated? So only one variable, that is the reason I write that is dx by dx. Now from f to y, how many from f how many variables are associated? 3 variables. Therefore I write dou f by, that is dou y. Then from y to x, how many variables are associated? Only one variable, that is the reason I write dy by dx. Plus here it is given as y prime, right, in the equation. So it is f is associated with 3 variables, so I am writing dou f and divided by dou z into dz by dx, right? And this is how it is, right? Or dou f by dou x is equal to df by dx is equal to dou f by dou x, dou f by dou y, and dy by dx I can write it as y prime, and as well as dou f by dou y prime, dou y prime divided by dou x I can write it as y double prime. So this is my equation 1. Fine. Also I know that d by dx of y prime, dou f by dou y prime, this is u or v uv rule, or first function second function, first function as it is d by dx of second function, and second function as it is differentiation of first, right? So this is equation 2. Now what I do is therefore on subtracting equation 2 from 1, so if I subtract this value, if I minus this value, so what did I get? So dou f by df by dx minus d by dx of y prime dou f by dou y prime. This is it. Okay. So then this two things I will write it at once. Dou f by dou x, dou f by dou y, y prime I am writing here, minus, see here, minus this term, right, minus y prime d by dx of dou f by dou y prime. Okay, and this dou f by dou y prime and this dou f by dou y prime, y double prime gets cancelled. So finally what do we have? We have d by dx. See, from here I take common outside, that is df by dx, and here d by dx, d by dx I take common outside. So inside what is left out, it is f minus y prime dou f by dou y prime. Okay, this dou f by dou x I will take it to the left hand side, minus dou f by dou x equal to, see, y prime I am taking common outside from here, so dou f by dou y minus d by dx of dou f by dou y prime. Now this equation is nothing but, what is this equation? It is in fact the Euler's equation, right, which is equal to 0. So finally what we get? So d by dx of f minus y prime dou f by dou y prime minus dou f by dou x equal to 0, which is another form of Euler's equation, right? So please have an eye on Euler's equation, which is very important in solving problems. Now we also have another form of that is Euler's equation. If this derivative, that is dou f by dou y, okay, is also a function of x, y, y prime, that is the derivative function, say phi of x, y, y prime, then we have on that is evaluation, that is again following the procedure of total derivative, and then finally after evaluating we get another form of Euler's equation, right? So these all the forms are important. Just have an eye on this. Fine. So this extremal can be obtained, that is the minimum and maxima can be obtained by solving Euler's equation, as already said that it is very important. Okay, now let us see certain cases which are also of immense importance while solving Euler's equation, which makes our work very simple. Okay, so when regarding f, whenever the given function is expressed in the term of x, y and y prime, that is dy by dx, when f is independent of x, right? So what will happen when f is independent of x, that is x is not available in the given function, right, or the expression, right? Therefore when f is independent of x, then dou f by dou x equal to 0. Therefore from equation 3, that is, what is your equation 3? This is your equation 3. So f is independent, obviously this equation will take it as 0 and will retain this equation, right? So d by dx of f minus y prime dou f by dou y prime equal to 0. Therefore on integrating we get f minus y prime dou f by dou y prime, which is equal to constant. Now when f is independent of y, so dou f by dou y equal to 0. Therefore from equation 2, that is your Euler's equation, right? Here it is. So dou f by dou y equal to 0. If I take this term turns out to be 0, then what do we have? We have, that is, t by dx of dou f by dou y prime equal to 0. Therefore on integrating, what do we have? Dou f by dou y prime, which is equal to constant. Now equation 3, that is, case 3, we have if f is independent of y prime, so dou f by dou y prime will obviously turn out to be 0. Therefore from equation 2, that is again by using Euler's equation, so we have dou f by dou y equal to 0. And finally for case 4, we have, if f is independent of xy, dou f by dou x equal to 0, dou f by dou y equal to 0. Therefore from equation 4 we get y double prime dou square f by dou y1 square equal to 0. Now at any instant, if dou square f by dou y prime square is not equal to 0, so it reduces to a solution, that is y double prime, or equation y double prime equal to 0, which gives you a solution of the form, that is y is equal to c1x plus c2x, where c1 and c2 are constants. So as I said, Euler, you should know Euler's equation. What is Euler's equation? And another two forms of Euler's equation. Apart from that, you should also know these conditions, right? That is case 1, when f is independent of x, when f is independent of y, and when f is independent of y prime, and when f is independent of x, y prime, right? So this is very useful while solving problems. So let us see its working procedure. So what is its working procedure? So given a variational problem, so you will be given a variational problem of this type, right? So variational problem of this type, so it is a functional, that is I of y of x over the integral, that is x1 to x2, and the function f is a function of x, y and y prime of this particular function. You need to find what? Extremum, right? And the necessary condition is what? That it should be equal to 0, which is also as equivalent to, that is, this is the reason why we are taking this Euler's equation. So it is equal to 0. So dou f by dou y minus d by dx of dou f by dou y prime equal to 0. Then after applying Euler's equation for the function, that is f of x, y, y prime, which will result into ordinary differential equation in y, and we solve for y using suitable method, whatever suitable methods which you have already studied in your previous semesters, solving that is ordinary differential equation with constant coefficient, then homogeneous, non-homogeneous, method of variation of parameters, and so on, right? Fine. So let us see these problems one by one. Okay. Now find the extremal of functional, that is integration from x1 x2 y prime of plus x square y1 square dx. Now let me consider this as my given, this, okay, that is this given function is equal to y1 plus x2 y1 square. Then you write the Euler's equation. So this given equation is independent of y. You have y prime, you have x, you have y prime, but you do not have y. So therefore what do you conclude? That the given equation is independent of y, right? So when it is independent of y, definitely your and that is dou f by dou x is equal to 0. Therefore, if I differentiate it with respect to what do I require? I require dou f by dou y prime. So if I differentiate this given function with respect to y prime, so it turns out to be 1 over here. Then it is x square as it is, keeping the other factors constant and differentiating it with respect to y1. So this becomes 2y1, right? This, right? Therefore, on substituting the above equation, the above values in 1, right? So what do we have? 0. It is d by dx of, and dou f by dou y prime is 1 plus 2x square y1, which is equal to 0. So this again on rearranging, that is, it turns out to be d by dx of 1 plus 2x square y1 prime, which is equal to 0. Therefore, on integrating with respect to x, what do I get? I get, if I integrate this, I get 1 plus, that is integrating, I get 1 plus 2x square y1 prime, which is equal to some constant, right? So what I do is I take this y1, yeah, I take this y prime, that is dy by dx equal to k1 minus 1 divided by 2x square, or dy by dx is equal to k1 minus 1 divided by 2x square. Since this k1 minus 1 is a constant, so y is equal to, therefore on integrating with respect to x, right, I get y is equal to k1 minus 1 divided by 2 integration of 1 divided by x square dx plus c2, and y is equal to k1 minus 1 divided by 2 minus 1 by x, that is integration of 1 divided by x square plus c2. Therefore, denoting c1 is equal to 1 minus k1 divided by 2. Therefore, the required solution turns out to be y is equal to c1x plus c2, right? So is it not of the form, see here, if you have an observation, is it not this equation in the form y is equal to f of x? Okay, now for this equation, the above equation is extremum or minimum. For this particular equation, that is the above given functional is maxima or minimum, right? Fine. And the given functional was given as x1 to x2, and whatever is your function, f is a function of x, y and y prime. This is the only strategy. You have evaluated this in terms of this, and to this function, to this equation, this functional value, whether it is extremum or minimum, it depends upon this function, right? Okay, now let me move on to the second problem. Find the function y which makes the integral which makes the integral, that is extremum. So this given equation is 1 plus x y1 prime plus x1 x y y1 square dx and extremum. So given f of x is this, and this I am writing in this particular manner, my Euler's equation. Every now and then I am highlighting it. So therefore dou f by, so let me see what is, so it is independent of y, so there is no y term in it, so it is independent of y, so dou f by dou y, which is equal to 0, minus d by dx of, so differentiation of y with respect to y1, keeping other factors constant. So here it is 0, here it is x, here it is 2x y1 prime. Okay, therefore on integrating, so on integrating what will happen, this becomes x plus 2x y prime equal to some constant. So if I take this y1 here as it is, so y1 is nothing but, I can write it in this particular manner, that is dy by dx k1 minus x divided by 2x, or dy by dx is equal to, I will separate this, okay, that is k1 divided by 2x minus x and x gets cancelled, so I write it as 1 by 2. Therefore on integrating with respect to x, if I integrate this with respect to x, it turns out to be y k1 divided by 2 integration of 1 divided by x dx minus integration of 1 divided by 2 dx plus c2. Thus y is equal to c1 log x minus x by 2 plus c2, where c1 is k1 by 2, and this turns out to be your solution. And again, if you have an observation, this is also in terms of f of x. This equation, for this equation, the above equation is you can the above functional is either it is extremum or extremum, right? Whether it is minimum or maximum, right? Okay, now let us have the third problem. Okay, fine. Now we have let me have one more example, that is third example. Find the extremal of the function x1 x2 y1 that is y prime square plus k y square and dx, right? So this is the functional as given. So this is my function f of xy, generally that is functional, and let me have this Euler's equation, right? So see here, now if I take, okay, what is not there, x is not there, so there is no question of taking, that is obviously dou f by dou x is 0. So when I differentiate my given function with respect to y, keeping other factors as constant, so this here it becomes 0, here it becomes 2ky, so I am writing 2ky, minus sign is here, minus sign is here, d by dx of dou f by dou f y prime, right? So dou f y prime, it turns out to be 2y prime, right? Since 2 is here, if I divide this by 2, it turns out to be, the equation turns out to be ky minus d square y by dx square, which is equal to 0. Now this, on rewriting, I will write it as that is here, this dx d by dx and y prime, it becomes d square y by dx square, right? This, on rewriting, I can write it as d square y by dx square minus ky, which is equal to 0, right? Or d square minus 1 is equal d square minus k y is equal to 0, okay, where d is d by dx. Now if I take the auxiliary equation of this, so if I take the auxiliary equation or the complementary function, sorry, not complementary function, auxiliary equation, so this is nothing but, this is, I will write it as m square minus k equal to 0, right? Now this, in fact, I can write it as m is equal to plus or minus square root of k, right? So now this second order differential equation, and the solution depends upon the value of k, right? So now whatever the value, see, there arises only three cases, whether the value is real and distinct, or you have repeated roots, or you have imaginary. When k is equal to 0, what will happen? It will turn out to be, you have, since it is a second order differential equation, you have that is 0 comma 0, so e power 0 turns out to be that is, the solution turns out to be c1x plus c2. When k is p square over here, then we have distinct roots, so c1 e raised to px plus c2 e raised to minus px. When k is minus p square, okay, it is not minus p the whole square, it is minus p square, so you get imaginary roots, so y is equal to c1 cos px plus c2 sin px. And depending upon the roots, how you evaluate, yeah, here it is. So depending upon the auxiliary roots, that this you have learned in your previous classes, okay. So how you write a complementary function? So see here, these are two distinct roots, 2 and 3, which are different from each other. That was my case 2, that is c1 e raised to 2x plus c2 e raised to 3x. Now here there is repeated roots, so how do you write it? It is c1 plus c2x e raised to 0x. In my case it was 0 comma 0 because it is second order differential equation. So c1 plus c2x e power 0, that turns out to be 1, so is this, right? And finally this equation, if you have in the form of x plus iy, that is e raised to 3x c1 cos 2x, this is how we write. But in my equation it is plus or minus p, so I have written c1 cos 2x plus c2 sin x, and that is the reason the output is in this particular form. Getting? Yes, so it depends upon the value of k. Now find the curve. Let me have the next question, and this time certain conditions are given. So find the curve on which the functional, that is 0 to pi by 2, right? So, and this is the given function, that is f is a function of f, x, y, and their derivative dx with y of 0 is equal to 0 and y of pi by 2 is equal to 0 be extremized, right? Now comparing the given functional with 0 to pi by 2, so the given functional is, that is y1 y prime square minus y square plus 12xy, and the given condition is y is equal to 0 to 0, y is equal to pi by 2 is equal to 0. So let me take the Euler's equation. Okay, so see here, so let me see what x is there, y is there, all the terms are there, right? Yeah, so all the terms are there. Let me take this Euler's equation. So dou f by dou y, partially differentiating with respect to y, keeping other constant terms constant, minus 2y plus 12x. Dou f by dou y prime, I require this and this, 2y prime, and d by dx of this 2y prime. So again differentiating it with respect to dou y, it becomes 2y prime, this, right? Therefore using one, what do you have, that is minus 2y, 12, that is 2y plus 12x, right? Here this thing I am going to write here, and minus d by dx of this, right? Yeah, which is equal to, this is 2, 12, 2, so if I divide it by 2, then it becomes minus pi x and this minus y double prime. So on rearranging, I can write it as y double prime plus y equal to 6x. Now this equation, that is here I can write it as that this is a second order derivative, so this d I can write it as d by dx, so d square plus 1 y equal to 6x. Now the auxiliary equation is, so whenever you are writing an auxiliary equation, you should always equate it to 0. So for this particular thing, I write my auxiliary equation in this particular form, m square plus 1, which is equal to, m is equal to plus or minus I. So the roots are imaginary. So when the roots are imaginary, so what do you have, that is c1 cos 2x plus c2 sin 2x, right? Fine, c1 cos x it is, here it is not 2, so it is only 1, that is x, c2 sin x. Now I want to find my particular integral. So general solution, how do you find? Y is equal to, that is complementary function plus particular integral, right? Fine, so here the given differential equation, the right hand side is some function, right? So this is of the type, so which you have already solved in your previous class. This 6 I will take it outside, and here it is a polynomial, right? So how to find this? So see here, so it is of the form 1 divided by, that is this is phi of x divided by, that is your pi into f of t, and this is a differential polynomial, right? So how to solve this? Let me go back to your previous sum. One problem I will explain you. Actually I could have skipped, but now yeah, so this is how you form, this is f phi of x, which is a polynomial in D, right? And this is your f of d, that is a polynomial in D, and this is any given polynomial in x, right? So let me have this example for you. So here it is, yeah, so this is my phi of x, and this is my d square, that is f of d, sorry, yes, okay, of this form. I need to find the particular integral. Now whenever you have equation of this time, a given polynomial is there and a differential polynomial is there, that is okay. So what I do, I always write this differential polynomial in ascending powers of d, that is small to big. So here it is usually that is d power 0, so it is I did not write, right? Okay, so this ascending powers of d, and this is whatever polynomial is there, you need to write it here, right? Here first. Yeah, so now take this first term. If I take this first term 2x square, and then you need to take this first term, so always have this habit. So this and this gets cancelled, so whatever is here you write it here. So x square, when you multiply this with this, that is 2x square is 2x square into 3 into d. Differentiation of x square is what? Differentiation of x square is, that becomes 2x once, and then 3 multiplied by 2 is 6x. Then see, this separately you need to do, right? So differentiation twice it is. If it is 4 here, then this answer turns out to be something different, that is 4 to 8, right? Now it is d square, this I will multiply with this, so twice if I differentiate this I get an answer 2, so I am writing here 2. Then after evaluating this, minus minus minus, these two terms get cancelled, so this is minus 2x minus 1. Then again what I do is, again I take this term, first term, this again I include this first term, that is minus 2x over here divided by, right? This term I take it here, again this first term, this gets cancelled, what I am having, minus x, so I am writing minus x. So 2 into minus x will be that is 2x yes. So 2 into minus x is minus 2x, and then 3 times differentiation of minus x once is minus 3, so I've written here, right? And differentiation of x twice if you do, that turns out to be 0, so I did not write it. Then again plus minus, these two terms get cancelled, you have 2. Now again take this first term, and then they take this first term of this, and then gets cancelled it up, and then what you have 1, so write 1 over here. Okay, and after evaluating again, that is 2 and 2, and differentiation of 1 is 0, so I did not write it. So whatever quotient you get, that turns out to be your pi, right? Okay, now in my case, or in our case, so this form you should remember. So what was the form? So this polynomial form you should remember. So in my case the problem was, yeah, it is 6x. 6 I am already taking out that x d square plus 1. So here it is x divided by d square plus 1. The first thing is I should write it in ascending powers of d. So 1 plus d square into x. So first term I will take as it is and divided by 1. So it is x only, right? Constant. Fine. Okay, so 1 into x is x, minus differentiation of x twice, it will be 0, so I did not write it up. So this is obviously 0. When this 0 arises, this is your quotient, whatever is this, so that turns out to be your pi. So here this is a quotient, that turns out to be its pi. Here this is a quotient, so that turns out to be its pi, right? So that is the reason, that then multiply it by 6x. Therefore the solution is cf plus pi y is equal to c1 cos x plus c2 sin x, that is your cf into 6x. Now using the condition, this is the value of x, this is the value of x, and y is equal to 0, y is equal to 0. Now in this equation, if I substitute y is equal to 0 and cos equal to 0, so cos of 0 is 1, sin 0, sin of 0 is 0, 6x 0, so it becomes c1 is equal to 0, right? Also when x equal to pi by 2, this turns cos pi by 2 turns out to be 0, 6 pi by 2 it turns out to be 3 pi, right? And it is sin pi by 2 is 1, so c2 6 pi by 2, so c2, and I will transfer this to the left hand side, so c2 is equal to minus 3 pi, right? Fine. And therefore an extremum can be therefore substituting the value of c1 c2, we have, that is y is equal to x minus 3 pi sin x. So again you have an observation that this equation is of the form y of x. So this, depending upon this equation for the above functional, we can find its extremum value for this given function, right? Now let me have another example. So I have to give you homework also, right? Yeah, find the extremal of the functional y square y1 prime square 2y e raised to x dx. Now this is your functional. So y square plus y1 square plus 2y e raised to x, right? So Euler's equation, I need to write it up, right? And see here, after evaluating, this turns out to be, with respect to y, it is 2y, then it is y over here, right? Y over here, so it becomes 2 e raised to x. So this is here for this particular thing. Now d by dx as it is, right? And differentiation of f with respect to y prime, so it becomes 2y prime. This is here, right? Okay. Now since everywhere here it is 2, so I can divide it by 2. So y plus e raised to x minus y, so differentiation again, if I differentiate this with respect to y prime, so again it becomes y double prime, which is equal to 0. Therefore on rearranging, I have y double prime minus y equal to e raised to x. So this is d square minus y equal to e raised to x. Now this is a standard form. This is a second order linear differential equation, which with the right hand side with the function that is e raised to x. First thing is, I need to find the solution of this given differential equation. So I take the auxiliary equation and equate it to 0 first. So the auxiliary equation of this, I can write it as, that is m square plus minus 1, which is, I am going to get my root as m is equal to plus or minus 1, which are distinct, real and distinct. So when the roots are real and distinct, so I can write my complementary function as c1 e raised to x plus c2 e raised to minus x. Now particular integral, now this is also one of the standard form in differential equation. So that is e raised to x divided by d square minus 1. Now this equation, yeah, see, this was the equation that any given equation of this particular form, e raised to ax. So what you do, you replace d by a. Okay, so this is a differential polynomial, this is a function e raised to ax. Now in my case it is 1, right? So at any instant, if this f of d is 0, then what you do, you differentiate this f of d and multiply the numerator by the variable, whichever variable is here, x. Again, if it turns out to be 0, then multiply it by x, it becomes x square, and again differentiate it, right? So here in the given problem, so what I do is, here I replace, that is d by 1. So when if I replace d by 1, so here it becomes 0. So to avoid this, what I do, I differentiate this given numerator again, so it becomes 2d minus that 1 is 0, and it is multiplied by x. So x e raised to x divided by 2d, which is equal to x e raised to x divided by 2. So this is your pi. Therefore the complete solution is given by, that is y is equal to cf plus pi. So c1 e raised to x plus c2 e raised to minus x, this is your complementary function and your pi. And finally, if you see this, is it not the equation of the type y is equal to f of x? See, the problems are so simple. Okay, the next problem is find the curve on which the functional z is 0 to 1 y1 square plus 12x y dx. So this problem you better take it for homework. But matter of fact, I will explain you, that is in a quick succession. That is, I is equal to this, and this turns out to be a functional. Then take the Euler's equation, right? Differentiate it with respect to y, d by dx of dou f by dou y, partially differentiate this given function. So this turns out to be 2y, so it is 12 here, it is that is 2, right? So this is d square y by dx square equal to 6x, right? Therefore here this equation integrating with respect to x, I get dy by dx 3x square plus c1, that is constant. Again integrating it with respect to x, you get y is equal to x cube plus c1x plus c2. Now using the condition y is equal to 0 and x equal to 0, and y is equal to 0 at x equal to 1, so c1 is 0 and c2 is 0. Therefore your answer turns out to be this, and this is the required curve for which the above functional is. It depends upon the this curve that the above functional is an extremum, right? So please go through the notes, and at any instant if you have any doubts, please let me know through text message or call me up and ask me the question, right? Please do not waste your time. Fine. Okay, now the next question is, that is, find the extremal of the functional that is x1 square y1 square minus y2 plus 2y sec x, right? So the given function is this, right? Y1 square minus y2 plus 2y sec x. Then write the Euler's equation as usual, right? So dou f by dou y, so y, this becomes minus 2y plus 2y, so this is 2 sec x, right? And that is dou f by dou y prime d by dx of 2y prime, it becomes, so equal to 0. Therefore here it is 2 2 2, I divided by 2, right? So on rearranging I get y double prime plus y equal to sec x. Now this is a ordinary differential equation, that is second order differential equation, but the right hand side you do not have a standard function or standard method to evaluate this, so or this phi of x. So there is one more method we need to apply, what, that is method of variation of parameters, right? So first thing is I need to find the auxiliary equation for this. So the auxiliary equation is, so I equate always to 0, so m square plus 1, right? This particular equation I can write it as d square plus 1 y equal to sec x, and this is m square plus 1, so m is equal to plus or minus 1. So the complementary function is c1 cos x plus c2 sin x. See here, so whatever so let me assume my solution to be in this particular manner. So I will consider this c1 as a and this c2 as b, and this is y1 and y2. So be the solution of differential equation where a and b are functions of x. Now method of variation of parameters at any instant, if some of you have not gone through it, so let me explain you in a quick succession. Yeah, so this is the concept you will find in any of the engineering books, or you can search online also, but matter of fact I will do it in a quick succession. This is a second order differential equation, right, which will be of this particular form, right? Yeah, phi of x. Now whatever depending upon the auxiliary equation you have roots, since it is second order differential equation, so you have two roots always. So whatever is that root, this c1 and c2 you consider, suppose my solution, whatever is this y1 is a function, it might be any polynomial like existing there, that is cos x, sin x, or x e raised to x, right? So I need to find the value of a and b. So how do you find the value of a and b? So this is all the procedure, right? So before do that I need to find so to find the value of a and b, you have this particular formula, right? But before to that I need to find the Wronskian, right? So Wronskian is given by, so you need to take the product of y1 and y2 prime and minus y2 and y1 prime, which is called the Wronskian of the function. So Wronskian of the function you need to evaluate it, therefore it becomes that is a prime is equal to, that is minus y2 phi of x divided by Wronskian, b prime is equal to y1 phi of x divided by the Wronskian. So similarly to find that is therefore this differentiation, it goes to the right hand side, or integrating both side you can take. So this is the formula to find the value of a and b, and this is the Wronskian of the function, and you know how to solve the Wronskian, right? Now let me have this is the working procedure, so you can pause the video and just have a look on it. So any given differential equation of this type, wherein the given if at all it is not a standard equation or form which you have already studied, so it is pi of x, we write the complementary function in this particular manner. Okay, we assume, so you should assume that your given function or the complementary function is of the type that is y is equal to a y1 plus b y2 to be the complete solution of the differential equation where a and b are functions of x. Then take the Wronskian, so you need to differentiate this, and then take the Wronskian of this, and finally you substitute in the given formula to find the value of a and b. Now let me have an example for you in a quick succession. Yeah, see, now this is a problem and this is your phi of x, right? So the given differential equation, I will write it in this form. Okay, so the auxiliary equation is equated to 0. You get two roots and the roots are repeated roots. When the roots are repeated roots, their complementary solution or the function turns out to be c1 plus c2x e raised to 3x. Now y is equal to this c1 is a, this c2 is b, and this y1 is what? E raised to 3x, y2 is x e raised to 3x. So let me consider this y1 as e raised to 3x and y2 as x e raised to 3x. If I take the differentiation, this turns out to be 3 e raised to 3x. If I take differentiation, that is UV rule, 3x e raised to 3x plus e raised to 3x. Then if I take the Wronskian of this, so it turns out to be e raised to 3x, and phi of x is e raised to 3x divided by x square. Therefore a prime is equal to minus y2 of phi of x divided by w, that is my Wronskian. And you have removed the Wronskian also, and b prime is, that is y1 phi of x divided by Wronskian. Now this e raised to 3x, this e raised to 3x, it becomes e raised to 6x by laws of indices. This gets cancelled, this x and this x square, 1x cancels, so it is minus 1 by x. Now this b is nothing but this and this gets cancelled, so it is 1 divided by x square. So on integrating, I get minus 1 by x dx plus k1, 1 by x square dx k2. Therefore a is equal to minus log x plus k1, b is equal to minus 1 by x plus k2. Substituting the above equation, that is the complementary solution. So this will give you what? This is your value of a and this is your value of b. That turns out to be your solution, right? Similarly, in my problem, so here it was sec x, right? So this is the differential equation and it is what? Imaginary root. Imaginary roots. So I can express my solution in terms of c1 cos x plus c2 cos x, or let me assume the solution to be a cos x plus b sin x, right? Now a is equal to minus y2, this is by the formula. I need to find the value of a, value of b, so this is the formula. So phi of x is sec x, Wronskian is y1 y2 prime minus y2 y1 prime, right? So y1 is cos x, y2 is sin x, y1 prime is, that is differentiation of this, is minus sin x, y2 sin x. If I take the Wronskian, it turns out to be 1, so which is now very easy to access. So a is equal to minus 1 sin x, sec x can be written as 1 divided by cos x, which turns out to be tan x, and integration of tan x is, that is this minus sign, log sec x plus c1. So 1 sec x can be written as 1 divided by cos gets cancelled, 1 dx, so x c1 x plus c2. Therefore the value of a is this into cos x, and the value of b is this, right, into sin x, and this turns out to be your solution, right? So this was all right. And now take these problems for homework, that is solve the variational problem with respect to the condition, right? And please show it to me in the class. If at any instant if you are not getting the answer, you can tell me, right? In my next class I will deal with the concept of applications of calculus of variation, which is as important. So that's it. Thank you very much.